I'm a research scientist at Google, and this work was done during my PhD studies at UC Berkeley in collaboration with Adobe Research and University of Waterloo. So previous talk mentioned about the hand postures. In this talk, we will focus on whole body movements. Illustrations of human movements are used to communicate ideas and instructions in many domains. In sports, dance, and body gesture interfaces, movement instructions are often used are often conveyed with drawings of the human body, annotated with arrows. So here, the figure on the left illustrates a kick of judo with a red motion arrow from the bottom pointing to the top, pointing to the end pose. And the figure on the right shows is from a Kinect game tutorial. It shows a jump with a double-headed arrow. So beyond showing a single motion, step-by-step movements can also be presented as a series of figures. Here, dance moves are highlighted with yellow arrows. So by looking into these figures, can anyone guess what dance moves these illustrations are? Put your hands up if you know the answers. That's a hint. Can anyone yell the name of the song? Yay! Yes. So it's Beyonce's Single Ladies. So actually, this illustration is so effective as we can just quickly take a glance and then identify the key movements. Illustrations of such human movements are actually also used within the HCI community to convey new user experiences. When designed well, these illustrations can precisely depict the motion while excluding unnecessary details like faces, clothes, or backgrounds. So both professionals and non-designers create this type of illustrations. But the methods they use are commonly time-consuming. The typical workflow is to design the physical scenes and poses and then photograph the actors. And then authors will manually sketch or trace the subjects from photographs to abstract the information. Finally, they can add the highlights, such as the motion arrows. Authors then repeat to create a series of figures. The entire authoring process can take up to several hours. And what if the authors decide to make some adjustments, such as to exaggerate the hand postures or change a gesture? This usually means starting over again with new source photos, and this makes it difficult to really iterate and quickly edit. But if we really look into this typical workflow, we can see authors commonly switch between the physical demonstration, which is to pose in front of the camera, and switch to the computer to create the illustration using the software tool. So in this work, we wonder, how do we really enable authors to rapidly create step-by-step illustrations through physical demonstration? We propose DemoDraw, a multi-modal approach that takes 3D skeletal data and speech input and render the concise motion illustrations. With DemoDraw, authors perform movements in front of the Kinect sensor, and 3D skeletal data of the user's physical motions is captured in real time. Meanwhile, the skeletal data is then applied to a 3D avatar directly. So I'm going to show a video here, and listen to the sound.
1, 2, 3.
So with this motion recording and the user speech data, DemoDraw automatically analyzes the motion data to generate this kind of step-by-step figures, annotated with the motion arrows that show the user movements. So users can just quickly create a series of illustrations from physical demonstration in front of the Kinect camera. Users can later move to a desktop computer to refine illustrations by changing the styles and parameters. So previous work has proposed offline methods to visualize movements showing the motion trajectories in various contexts. However, these methods do not really support iterations between user specification and visualization. As we aim to design a tool for users to quickly test out the movements and see the results, we've designed an iterative workflow. Users demonstrate their physical movements in front of the camera, They also provide some speech labels to annotate those motions during our demonstration. And based on the skeletal data and speech data, DemoDraw creates the illustrations and replaces the data with distinct motion arrows for authors to review. So authors can just, on the scene, navigate and reperform the moves if needed. And finally, they can do more refinements using our Refinement Interface. So let's look into the authoring process, the authoring components of DemoDraw. DemoDraw captures users' skeletal data of 25 joints in a 3D space. It then applies to the real-time data to an avatar, as the video is showing here. This is the user interface view that the user is moving around, and the avatar is like following the user. So given a series of continuous 3D motion data, we then want to segment a recording to useful steps in order to visualize the movements. However, automatic segmentation can be really challenging, especially for free-form movements like dancing. So we're inspired by how dance instructors verbally and physically explain their step-by-step moves in practice. So here's one example.
So we have 1, 2, 3, 4, 5, 6, 7.
So imagine how much time it might take for you to handcraft the illustrations from these dance moves. So similarly, with our demonstration interface, users specify the movements using speech, such as 1, 2, 3, and 4. And during the demonstration, so I'm going to show a video here.
3, 4.
Here we start by a simpler example, but later we'll show more complicated cases. Now, given the motion recording and a list of speech labels, our goal is to segment the motion and find the salient joints to visualize. Here, for example, the left and right hands are our targets. For each speech label, we examine each of the major joints, such as the left hand, by analyzing the continuous changes of the absolute 3D positions. We identify the salient changes for this joint, and we repeat for all the major joints, including right hand to the right foot. And finally, we combine the significant changes, which will give us the joint set, here, the left and right hands, for example, and the segmentation boundary, which is the start and end times. Other non-moving joints, such as the feet, here will not be applied. So in this way, we segment the motion recording, and we can create the motion illustration of this step. We select the final pose as the key pose based on existing design principles. Then for each salient joint, we render the motion arrow based on the motion data of this segmentation boundary. And we construct a 3D polyline and 3D cones as the arrow, but shaded to look like 2D. So we repeat this process to fully segment all the movements for each speech label and create a series of motion illustrations. Now, users can review and replay the results in front of the camera. And we implemented our system in Unity 3D. The avatar and all the motion arrows here are all the 3D objects that can be manipulated, such as to change the viewpoint and rendering styles, etc. So, still standing in front of the camera, reviewing the results, if the user is not satisfied with her performance of a specific step, such as step number 5 here, she can simply reperform that specific step without redoing all the moves.
Retake. Five. Stop. Play.
So our system automatically identifies the segment and replaces it. Finally, authors can move to a desktop computer to do more refinements using mouse input. She can change the arrow styles, including the size, line width, and colors. She can also reveal the original capture data to examine. And we also support direct manipulation of the arrows, where users can just drag their arrows, which can be useful for more detailed refinement. And finally, rendering styles can be changed, such as to change into a silhouette or color, or even to change in 3D avatar. Here shows more example results generated by our system, showing different rendering styles and viewing angle. In addition to motion arrows, we also explore different visualization methods. Here, stroboscopic effect is useful to convey the ordering of the movements. This is again from a Kinect game tutorial. Since our system captures the entire motion recording, it can easily create these effects by selecting just several frames within a step and changing the offset and the transparency. And combining a stroboscopic effect with motion arrows may also help convey the start and end poses. Alternatively, a stop motion diagram can be also effective to show a sequence of movements. Again, we can create this by changing the offset between the figures within a step segment. All in all, our approach makes it easy to quickly generate a gallery of examples of different styles. Sorry. Oh, damn. I'm like, why is it so wet? Right. To evaluate our system, we conducted 3 studies with 14 participants. Our study, let me just carefully move here. This is horrible. Right.
It's okay.
Our first study evaluates if users can understand step-by-step motion illustrations that our system generates. So we show these 2 4-step figures to participants and ask them to interpret and perform the movements. We coded each joint movement to examine 3 things. If the visualized joint was moved, and the start and end positions were correct, and if the movement was correct. So we found that our motion illustrations were effective as participants quickly and correctly performed most of the movements. But there are 4 motions that introduce some different interpretations, including the repeated actions, such as waving. So some participants just wave once, and some more detailed movements, like moving hands outward instead of inward. So in a later study, we'll introduce alternative designs. And our second study evaluates if users can efficiently create step-by-step motion illustrations using our demonstration interface. The experimenter physically performed movements in front of participants and asked them to practice, record, review, and reperform. For the first task, experimenters show 4 gestural interface using one hand. So I'm going to do a quick demo here. It's the waving action, making a circle, making a V, and swipe to the right. And here's one result from one participant, and another result from different participant. And for task 2, experimenter show 8 moves involving more than just one joint. Again, I'm going to do a quick demo. Let me quickly walk here. So it will go 1, 2, 3, 4, 5, 6, 7, 8. And we can see just by doing the demonstration, our system can generate figures like this. So finally, for the final test, we also provided an open-ended question to ask participants to record a set of free-form movements as they like. Here, P5 perform music conducting movements, like this. And P8 focus also on the hand movements, but different orientations. And P10, who is a dancer, perform more complicated whole body movements. So on average, participants created 4 sets of 4 to 7 step-by-step illustrations in just 22 minutes. And participants said the system saves significant amount of time creating illustrations. And without the voice capability, the system can be impractical in any single person use case. So finally, we want to see how users can refine using our system. So similarly, we ask them to perform record, and use our system to do more refinement. We found that providing a tool that enables authors to generate different styles is important. Participants have strong preferences once the tool enables them to quickly explore alternatives. So here, figure B helps show the progression of the hands while squatting down. And figure C shows the start and end poses. And figure D here conveys the sequencing. So all in all, our user studies show that users are able to quickly create different styles of motion illustrations using our system, and the results are expressive. Finally, we want to point out some opportunities. Many illustrations focus on motions while holding or manipulating objects, such as furniture assembling tasks. They may involve multiple users, and callouts might be added to show a more detailed view. Recent research has proposed fine-grained 3D tracking of hands, humans, and objects. However, automatically identify the right viewing angle and the levels of details still remains a research question, and we leave this as future work. So in this talk, we presented an approach for novice users to quickly generate human movement illustrations by physical demonstration with their motion and speech input. Our DemoDraw system supports recording, reviewing, rotating, and refining those motion visualizations iteratively. And with that, I'll be happy to take any question. I also need to clean up my laptop.
Time for one or two questions while I clean up.
Is there any napkins? This is horrible.
You answer the question.
Okay. Yes. Any question? Thank you.
Okay.
Any question?
Hi. Hi.
Hi.
Forrest here from University of Illinois. So I'm just wondering what's the granularity of the motion that the system supports? Can it be used in applications like generated tutorials for sign languages?
That's a great point. That's actually one of our motivations, as there are tons of sign language tutorials. So currently we rely on the Kinect technology. So whatever Kinect can track, then we can visualize. So the granularity depends on the accuracy that Kinect can track. So for example, torso is a little bit more difficult, but for all the movements, for sign language, if it's not about fingers, now currently yes. But there are also actually a lot of SIGCHI papers now do the fine grain like hand gesture recognition. So that's also possible. And we actually think sign language is a great application, as sign language usually do the actions while annotating the words at the same time. Because for example, like up or down. Yeah. So that's great application. Thanks.
Okay, let's thank our speaker again.